photo-assisted depollution. And today's talk, it will be related to these mentioned topics of major focus currently for both scientists. So Jean-Charles and Hugh, please take the stage.
Thank you, Olga, for this kind introduction, and thank you for giving us the opportunity to present our work dealing with nanodiamonds for photocatalysis. So we started in the nanodiamond field in 2010, and we investigate a lot the surface chemistry of the nanodiamonds. The goal was really to reach a very good control of this surface chemistry, and so we worked a lot on hydrogenation of the nanodiamonds, and then we transfer that for tritium labeling. Why? Because first, it's allow a quantitative measurements of the number of atoms we are able to graft on the surface or to insert in the diamond core. And also because we target bioapplications. And for bioapplications, the biodistribution studies are very important, and tritium can allow these biodistribution studies. So as I said, we target bioapplications, and so we functionalize nanodiamond first by peptide nucleic acid, and the goal was to target DNA. And a second kind of study was to play on the charge of the nanodiamond to electrostatically graft a small interferent RNA and then deliver this species. And this was a collaboration with biologists from EGR. And so in parallel, we evidence some interesting property of nanodiamonds, which could be active under X-ray or gamma ray irradiation, especially active in producing some radicals in water, for example, hydroxyl radicals, or even scavenge those radicals if you change the nature of the particles. So 5 years ago, we moved to a new laboratory at CEA, as Olga said before. And so our goal today is really to go on the control of the particles, so their surface, their core properties, to link that with the colloidal behavior of these particles, and also always motivated by specific interaction between light and nanodiamonds. But the target for application is new. It is related to energy applications. First, solar fuels production, so hydrogen or reduction of CO2. And the second one is more in the environment applications with pollutant photodegradation. This work will be presented by Hugues just later me. So let's start with the context for photocatalysis with the bulk diamond. So this is a specific semiconductor in that sense that the band structure is very sensitive on the surface chemistry. And you know, I mean, probably all this work showing that when the surface is hydrogenated, you got a shift of the whole band structure by 1.5 electron volts. And so in that case, if you illuminate in the deep UV and promote electrons in the conduction bands, these electrons will be very strong reductant. And Hammer's group showed that these electrons, the solvated electrons, can be used to reduce nitrogen or even CO2. What about nanodiamonds? Few years it's quite recent, and 2 or 3 years ago, and this is a work on the Prague's group, they evidence by a UPS XPS study that for nanodiamond, we have similar behavior. So this sensitivity on the surface chemistry to shift the band structure. And so based on that, there were some proof of concept using the UV range. So this is the first one was also the Hammer's group using hydrogenated milled nanodiamonds for CO2 reduction. And more recently, this is an American group also, Maza and co-workers, showed that it's possible to use hydrogenated detonation nanodiamond to degrade organic molecules. what about the visible? And if we look to the recent literature, we can see some studies that suggest that nanodiamond can be active in the visible range. The first one was using hydrogenated detonation nanodiamonds in the visible range, so 400 nanometer. And this study showed that this nanodiamond can generate solvated electrons in the visible range. This is, according to the author, could be related to sp2 carbon present in the particles or even defects. Then hydrogen production, we reported, this is our group work together with Strasbourg, we reported hydrogen production using oxidized detonation nanodiamond under solar irradiation. And very recently, it was last year, the Japanese group showed that CO2 reduction can be achieved if they use detonation nanodiamonds with a high nitrogen content in. So now, what kind of nanodiamond are available? The two main available in terms of amounts are the milled material first, and also the materials obtained by detonation synthesis. But recently, if we look at the state of art for the synthesis, different bottom-up strategies appears. The first one, based on a high pressure, high temperature, starting with molecular DOIDs, and then achieving very good crystalline quality, controlled diameter, doping, and color center. In parallel, the chemical vapor deposition also provide very good materials. The point is that for these strategies are not mature in terms of amounts. This is why the study we are presenting today are mainly focused on the milled nanodiamonds and detonation ones. So we will start with the detonation nanodiamonds, well-known material, I would say, in the community. So there are defects in the core, as you can see in this high-resolution TM. You can tune the surface chemistry using gas phase treatment, and these are the fingerprints you can get on infrared and XPS experiments. So briefly, you see in the infrared that for the oxidized particles, you have all the features related to carbon-oxygen bonds at the surface, while for hydrogenated, you reduce strongly there's a contribution and you have the CH signal here. Looking at the XPS, it's interesting to see that for these particles, we have a component related to defects, which is very important in terms of quantitatively important. And on these particles, when you apply the hydrogenation, you reduce very strongly the oxygen concentration and also the carbon-carbon sp2 contribution from 4 to less than 1%. Both surface chemistry can be suspended in water, this is well known, and you got the expected zeta potential, the negative one for the oxidized particles and the positive for the hydrogenated one. Looking at the milled nanodiamonds, something very particular is observed. This is the very good crystalline quality of these particles. You can see here a high resolution TEM picture of such a particle. And recently, we have done, together with Arsène Chemin, Tristan Petit, and Alan Hoffman, some experiments, NEXAFS experiments, comparing different hydrogenated materials, detonation, milled, and polycrystalline. And if you look at the carbon KH, you can see that for the milled hydrogenated nanodiamonds, we were able to see clearly the diamond excitant, quite perhaps a little bit lower than the one of the polycrystalline, but it's not possible to see it on the detonation hydrogenated particles. So very good crystalline quality, and on such particle, you can also tune the surface chemistry. So the oxidation or the hydrogenation, you have here the IR and XPS fingerprints. Perhaps I will focus here on the XPS. So for the oxidized particles, you have an oxygen concentration more than 9 atomic percent. You see that you have also sp2 carbon that is very significant in these particles. And the main component in the XPS is related to the CCSP3 diamond lattice. Switching to the hydrogenation, you see that we lose the oxygen. The concentration is now less than 1 atomic percent, and also the sp2 is considerably reduced to less than 1%. So looking now on the colloidal properties of such milled nanodiamonds, you can also, with these particles, obtain the zeta potential I mentioned before for the detonation particles. But we look more closely on the spatial repartition of the particle in the water using cryomicroscopy. So this is a large-scale image. And you can see, and this is something very interesting, that these particles are forming chains, but over micron size chains. So if we look inside more closely, we can see that these chains are formed by facet-facet interaction. So this is something very interesting and specific to hydrogenated milled nanodiamonds. Another interesting property, and I will come back to the IR spectra, is related to a surface conductivity. So this curve compares milled hydrogenated nanodiamonds in the sediments and in the supernatant. So on the top, particles stable in water, in the bottom, the sediments. And you can see that if you compare in detail the spectra, you see here a specific feature that is really related to the particle able to be suspended in water. And the position is corresponding to the Raman first-order diamond mode. So this was observed by several groups, including ours, and it has been attributed to a Fano effect and to destructive interference, and related to a surface conductivity on their surface. And this was confirmed by measurements on the Prague's group, quite in the same period. And you can see here the conductivity measured for different nanodiamonds. So HPHD milled particles of different sizes, hydrogenated, compared to detonation hydrogenated. And you see that if you consider the hydrogenated detonation nanodiamond, you will lose this surface conductivity of more than 4 orders of magnitude. So this is interesting for us. It suggests some surface transfer doping. So to investigate that, we perform an in situ UPS XPS spectra on these particles. And so we started with these particles sprayed on a gold silicon substrate. And this is the condition of the initial substrate. So we rebuilt the bond structure. And you can see that for the initial hydrogenated milled nanodiamond, we have this negative electron affinity expected for bulk diamond, and a location of the Fermi level very close to the valence band. This suggests a p-type doping of the sample. So in situ, we perform 2 annealing and then measurements of the sample. And you see that we lost this negative electron affinity after the first annealing of 200 degrees C. And also, we have lost also the p-type character. Then, if the sample is rehydrated and measure again, you see that the situation is very close to the initial one in terms of negative electron affinity. There is some difference in the position of the Fermi level, but this suggests that it's a reversible phenomena, probably due to adsorbates. So, of course, we cannot say for the moment what are the adsorbates. We have different candidates, but we are, to be honest, we are also thinking about some specific interaction with water molecules. So to see that, we would like really to probe the shallow surface of these particles. And to do that, we contact the synchrotron, the Soleil synchrotron just close to here. And so we write this proposal. And this proposal was to be able to form a nanodiamond beam. To do that, we have here the know-how with our colleague Olivier Sublementier. He's able, from a colloid, to form an aerosol of nanoparticles. After drying and then use this aerodynamic lens, you can get this focused beam of nanoparticles. So this focused beam can cross the photon beam, and photoelectrons are selected and analyzed in energy. So this is XPS on hydrated isolated particles, as you will see. And of course, compared to the conventional XPS, due to the tunable energy of the photons, you can probe very shallow surface. And in this study, we probe between 0.3 to 0.5 nanometer. What are the results? First, we obtain expected electron affinity for both particles. So for the hydrogenated MND, we still have the negative electron affinity while it shifts to positive electron affinity for the oxidized particles. And if we see more closely what is the carbon 1s signal compared to, so you have the conventional in red and the synchrotron in dark, and you see that due to the probe depth, it's very weak, you see that in the region assigned to carbon-oxygen bond, we have a signal that is higher compared to the conventional XPS. So, and even you have all the details here of the fit between the conventional and the synchrotron, you have something like 40% of the C1s peak that is corresponding to carbon-oxygen bonds. And this surface chemistry is comparable to the oxidized MND we measured in the same conditions. So the point is, why do we have these oxygen functional groups? And so for the moment, the hypothesis we have, but we have to prove more, is that it could be related to a dissociation of water molecules on the hydrogenated surface of the mid particle. This phenomena has been seen for hydrogenated bulk diamond before by Alan Hoffman group. So to conclude and then to give the floor to Hugues, we have two main nanodiamond materials, the detonation one with the defective core. As it is hydrogenated, we lower the sp2 carbon in the oxygen at the surface, and we got stable colloid for months. It is important for photocatalysis experiments. For mild nanodiamond, you have this excellent crystallinity of the core. As it is hydrogenated, you also have low sp2 and low oxygen, and you have additional properties, so the negative electron affinity, the surface conductivity, and specific interaction with water. And we also have stable colloid in water. The question is now, which photoactivity? So I will switch and give the floor to Hugues.
Thank you. Thank you, Jean-Charles. So, and thank you for this very nice introduction on all the material that we can. Okay, I'm just trying to find my. Oh, just give me a second. Okay, do you see? Is it okay, Jean-Charles?
I don't see it for the moment.
Not?
Not me.
Okay.
Olga, did you see?
Of course. Okay. Let me try.
Otherwise, I can share and then.
Sorry, I'm gonna try another. Okay. Like.
Yes.
Okay.
It's yes.
I just need to move it a little bit. I don't know why. Okay. Sorry for the interruption. This is okay? You can see it?
Yeah, it looks great.
Okay, thank you. Okay, so thank you, Jean-Charles. Sorry for the interruption. So the idea here now is to look at the photoreactivity of all these kind of nanodiamonds. As Jean-Charles already explained, there is the mild nanodiamonds, also so-called HPHT nanodiamonds, and the detonation one. And in the second part of the lecture, we wanted to show you two studies that we conducted the last years. The first one will deal with the production of hydrogen, the photocatalytic production of hydrogen. In the second one, we will show what we obtained very recently in the context of the photodegradation of polyfluoroalkyl molecules. So I'm sure that you are all aware that we can have production of green hydrogen from the photocatalytic dissociation of water into hydrogen and oxygen. So this is so-called water splitting. But in our case, due to the design of the photoreactor that we can use, we want to avoid the production of the oxygen. So what usually people is doing when you want to make hydrogen, a photocatalytic hydrogen production, is that you're going to use a sacrificial reagent which will consume all the holes which are produced at the valence band. And for instance, you can use an alcohol. So in our case, we use the 3-ethanol amine alcohol, but you can also use some methanol. And by this oxidation, then you're going to scavenge all the holes, and you're going to keep only the production of hydrogen from the reduction of the protons at the conduction bond. And so here is the system that we used. So at the time we were collaborating with a group in the Strasbourg University, and this is a quite conventional system for the photocatalytic studies. This is a photoreactor in which you have in the photoreactor the solution in which is dipping a lamp. So in this study we used a metal halide lamp which mimic quite well the solar illumination. So the idea is to have a gas bubbling with inert gas in the photoreactor. Then if you produce some hydrogen, then you're going to be able to measure and monitor the hydrogen production using a gas analysis system, which can be micro gas chromatography, equipped or not with a mass spectrometry. So the good point of this approach is that you don't have post-mortem study. You really have inline measurement of the production of the hydrogen. So this is a typical measurement that you can do with this system. So first you can see that you're going to be able to follow the production of hydrogen according to time. So when the light is switched off, of course, nothing happens. But as soon as you switch on the light, then you're going to have the production of hydrogen. Here, this is what we call the background hydrogen, because when you have this alcohol in the photoreactor, then you're going to have a photooxidation of the alcohol, which will give you a little bit of hydrogen. So what we want to look at is the difference between what you're going to obtain when you're going to add the photocatalyst compared to what you have initially without the photocatalyst. And in that case, this is really the overproduction of hydrogen that you're going to measure. So here are all the samples that we tested, so I will not go back into all this detail. Jean-Charles already explained to you all the differences in terms of surface chemistry, zeta potential of this nanodiamond. What I just wanted to stress out is that we compared detonation and mill nanodiamond prepared the same way, and all were perfectly stable in colloidal suspension. So in this slide, I prefer to summarize all the study to be able to quickly give you an overview of the result. But of course, you can find all the curves in this paper. So what is important to see here is that you have the comparison of the overproduction of hydrogen in presence of different types of photocatalysts. So with the titanium dioxide that we used as a reference, because this is a very standard photocatalyst that you can use for any kind of photocatalytic reaction, or at least for lots of different types of photocatalytic reaction. And you can see that we have this overproduction of hydrogen. And the good point is that we observed that we have a similar or even a little bit better overproduction of hydrogen in presence of oxidized detonation nanodiamond. And what was quite surprising at the time is that finally, using hydrogenated detonation nanodiamonds, on which we could have expected some more fancy features like the solvated electron production and so on, but finally, we don't have any overproduction of hydrogen. What you see is that there is no production above the background of hydrogen due to the oxidation of the alcohol, the sacrificial reagent. And then when you look at the milled nanodiamond, finally, in both cases, what you have is more inhibition of the production of hydrogen. It means that in presence of the two kind of milled nanodiamonds, you prevent the photooxidation of the alcohol, giving some hydrogen. So this is, for us, it was quite a major result. Of course, we wanted to be sure that it was not due to some contamination, because we all know that in detonation nanoparticles, we may have some metallic contamination. So we tried, of course, the repeatability of the measurement of independent batches of the same kind of detonation nanodiamond. You can see that the results were really reproducible. And also we tried with different source of nanodiamond. So here, for instance, you can see that for all the study, we use particles from plasma chem that we oxidize by ourselves with our own method, but we compared this with particles from adamas. So we use the oxidized particles as received, but you can see, but even as received, without any further oxidation, you have this overproduction. While if we used the positive zeta particles from adamas or particle from adamas that we hydrogenate by ourselves, you can see here that we have no more production of hydrogen. So, of course, this result raised two main questions. So, first one is how nanodiamonds are really, why they are able to absorb solar type light, okay, and the second one was, okay, while it is restrained only to oxidized detonation nanodiamond, while this type of nanodiamonds for which we observe photocatalytic hydrogen production. So to be honest, we don't have really the answer today, but maybe we can have a look in the literature to try to find some clues. If you look at the literature, and Jean-Charles already explained that, you can see that finally there is a role of nitrogen, which can be important to help for to absorb the light, also sp2 carbon and defect inside the detonation nanodiamonds. And more recently, also the Hammers team published a paper in which they showed that finally, even with oxidized bulk diamond, you may have some production of you may have some solvated electron emitted in water, even for sub-bandgap wavelength. And so if you look at all the characterization of all the type of nanodiamonds, finally what you see is that the oxidized detonation nanodiamonds may be gathered all these properties on the same time of particles, I mean high nitrogen content, present of sp2 carbon, and a very defective core. So this is so far what we think is at the origin of the production of photocatalytic hydrogen in presence of this detonation nanodiamonds. But also another thing to, of course, to take care is in terms of bond alignment, because as for any kind of semiconductor, you also need to have a good position of the conduction and valence bond if you want to make some hydrogen from the protons, and also if you want to oxidize the water, which will give you some protons also. And you can see here that also the alignment for the oxidized detonation nanodiamonds is favorable for these two kinds of reaction. So in this study, finally, we were able to show that with detonation nanodiamonds, we can produce some hydrogen. So the perspectives are to continue to go on this topic with our homemade photocatalytic setup here at the CEA that we built 1 year ago. This setup is able also to make some isotopic studies. So we want to have a try into heavy water to really define from where comes the protons. Of course, we can play also on the illumination source, and what we want to do is to look at much more complex DND surface, like with more sp2 carbon at the surface. At the same time, we also want to build more, let's say, complex system, diamond-based system with the addition of co-catalyst. This is what is usually done with titanium dioxide and all the other types of photocatalyst, and so we started last year with a PhD, and we are working on gold decorated detonation nanodiamond system, for which we start to have very good results. So here is the paper in which you can find all the detail of this study. So now let's move to the second part of this part of the lecture, which will be focused this time of the photodegradation using the nanodiamonds of this pollutant, the polyfluoroalkyls, that of course you are all aware of. And the idea, of course, comes from this pioneering work from the team of William Mazza in the US 2 years ago. So, very nice paper in which this team first showed that from the detonation nanodiamonds hydrogenated, they were able to see also some solvated electrons, which confirmed that what was previously also observed. But the point is that they used these solvated electrons to degrade one type of PFAS, which is the polyfluorooctane sulfonate, the PFAS, and they used for that a light centered at 254 nanometers, so quite deep UV. And the evidence also that the mechanism of degradation is based on a solvated electron mediation to break the CF bonds. And so starting from that, we thought about quite some open question. Okay, what about the nature of the nanodiamond? Finally, if we play on the milled or detonation, what can we have? What about the solar type illumination? Because we have seen previously that it was possible to have hydrogen with a solar type illumination. And also, can we go up to a full mineralization of the polyfluoroalkyls? So in this study, we focused on the perfluorooctanoic acid. This is another kind of PFAS, which is also definitely an issue, which has been produced a very large scale. We tested a large panel of nanodiamond, the milled, the detonation, the different surface chemistry. We used for this study a xenon lamp, which mimic quite well as also the solar spectrum. What we did is that we mixed a PFOA nanodiamond in water, and frequently, every 10 or 30 minutes, we made a sampling. We removed the nanodiamond and we analyzed the remaining PFOA and all the subproducts by HPLC mass spectroscopy system, and also we monitored the formation of fluorine ions by ionic chromatography. So this is the result. So this is a very recent study. I think this is the first time that we show these results. You can see here that you can follow here the amount of PFOA, so normalized to 1, so to the initial concentration. You can see here when we start the light on, okay? When there is no photocatalyst, of course, nothing is happening because you cannot destroy or attack the PFOA with only light, of course. But then after, if we had a little bit of oxidized detonation nanodiamond, you can see that we have a little bit of adsorption of detonation of PFOA at the surface of the detonation nanodiamonds, but then after there is no real photoreactivity with them, so different behavior compared to the production of hydrogen. Then we also tested the oxidized milled nanodiamond. You can see here that there is even this is even worse because we don't have any absorption of PFOA at the surface of the oxidized milled nanodiamond, and then after no reactivity at all. But when we used detonation nanodiamonds, hydrogenated detonation nanodiamond, as in the pioneering paper of Mazza, then we were able to reproduce the effect with this very nice decrease of the concentration of the PFOA, which is measured all along the exposure time, okay? But in that case, it is important to say that it was not with a 254 nanometer lamp, it was with a solar type illumination with our xenon lamp. And what was very nice is that finally, if you play with the type of nanodiamond, so with the milled one, then you can really increase the efficiency of the system. You can see here. So at the beginning, you have a very strong adsorption at the surface, which really helps to degrade the PFOA. And as we tested also, this is really also improvement of the degradation efficiency thanks to this milled nanodiamond. Then We also, of course, studied the effect of the concentration. So, of course, if we increase more and more the concentration of the milled nanodiamond, you will increase the efficiency. And finally, at 1 milligram per milliliter, which is not that much, finally, we obtained 100% of degradation of the PFOA in less than 40 minutes. And if you look in the literature, if you compare with comparable conditions like the concentration of PFOA, the solar type illumination, and so on, this is a very excellent result. So these nanodiamonds are really promising for that. And also, which is important, is that it is still highly efficient even in presence of air, because all the experiments were done under argon, but we tried without bubbling under argon, and we observed that finally this is not an issue. It can work also in aerobic conditions. Then, of course, we tried the reusability of the system, which is also very good. So here it means that after degrading all the PFOA, we keep the same nanodiamond, we just remove the PFOA, the subproduct, and then we put back fresh PFOA, and you can see that you can repeat the experiments without without any modification of the efficiency. So what about the subproducts? Because up to now, what I presented was the consumption of the PFOA, but then after you're going to have all the subproducts, which are also an issue. And what we observed, I will not go into all the details, is that what we have a quite standard chain shortening. So it means that we go from the C8 molecule to the C7, C6, and so on progressively in time. But also what is really specific to the milled nanodiamond that we are not able to observe with the detonation one is that we have another mechanism in which you will have a substitution of the fluorine by OH group. So it means that we have a parallel mechanism, and this is really related to the production of solvated electrons, as we found in the literature. And then using some competing reaction with scavengers to really elucidate if the holes or the electrons or the superoxide ions are really useful or not, we are able to show that finally all starts with the solvated electrons. But then after, if you want to go down to the full mineralization, you need to have also oxidizing species, especially the holes. So there is these two species which are really important, not only the solvated electron, but also the oxidizing part of the nanodiamond. And so I mentioned that we are able to fully mineralize. So here are the results. This is ionic chromatography. And you can see that we can go up to almost 100% of fluorine. So it means that all the carbon-fluorine bonds were broken. And it happens quite fast after only 100 minutes for the high concentrated nanodiamond suspension. And also we had to look at a little bit more closely to the wavelength responsible of the effect. And what we observed is that we only require UVA and UVB, so it means between 280 and 400 nanometers wavelength to activate the phenomena. Okay, of course, if you had a little bit more deep UV, you're going to accelerate the effect. But even with only UV which are present in the solar spectrum, you will have the effect, which is really good. So with that, I will conclude on this part on the photoreactivity of the nanodiamond, which is important. You can find all the details in this paper, and we just submitted a paper for the PFOA, the photodegradation, but you can also find the result on ChemArchive. And so the question now is, okay, what about the charge carrier dynamics in these particles? And now I will leave the floor now to Jean-Charles to continue this lecture.
Thank you, Hugues. So I will come back with the last part of this work. So I hope you can see my screen.
Okay.
So to investigate the photoactivity of this nanodiamond, we use this technique named time-resolved microwave conductivity. So what is the principle? So the sample is a powder. So usually all the first results I will show concern powder just after the gas phase treatment, so oxidation or hydrogenation. this powder will be exposed to a microwave field, and at the same time, a pulsed tunable laser can illuminate the sample. Of course, if you generate charge carrier in the sample, the conductivity will change and it will affect the reflected microwaves. And this is the signal you will detect, amplify, and be able to measure. So this is a typical curve obtained for other photocatalysts, so the TiO2, for example. So you have at the 0 time, you will have the laser pulse. You will initiate a charge carriers here with this intensity peak. And then versus time, you are able to to monitor the dynamic of carriers with recombination or trapping in the material versus time. So this was currently and frequently used to characterize photocatalysts. And in the literature, we were able to find only one study using it for nanocrystalline diamond films. So what will give these techniques on the nanodiamonds we have prepared before and with the performance Hugues showed just before. So I will start with the detonation nanodiamonds, so either hydrogenated or oxidized, and you have the TRMC signal we were able to measure in the UV range or in the visible range. And the first point is that the oxidized detonation nanodiamonds don't exhibit any photoactivity in the TRMC signal. This is something that raise questions. You remember that for hydrogen production, these were the most powerful particles. But when you look at the photoactivity in these conditions, you cannot measure any signal. The only signal we can measure concerns the hydrogenated detonation nanodiamond. This is a signal you can see here. This is reproducible. We have reproduced it on several samples. But you can see that carriers probably recombine very quickly because you don't have this behavior shown for the TiO2 before. So what happened when we switched to the milled nanodiamond? So this is what we got for the milled nanodiamond in the UV and in the visible range for the two surface chemistry. For this particle, the oxidized particles cannot show any photoactivity. But if you look at the hydrogenated one in the UV range, you see the typical signal of a semiconductor. This looks like to the TiO2 signal I showed before. So this means that in that case, we have really the semiconductor behavior we expect in the UV. Nevertheless, when we look in the visible range, the signal is very close to the detection limit, as you see here. So this is what we got for the four kind of particles. But there is an additional result. I said that all the previous measurements were done on the powder just after treatment. And then for the hydrogenated particles, we compare these particles you have seen before, so extracted from the hydrogenated powder, with the one that were suspended in suspension, then dried and measured. And as you can see in the UV range, we have a very significant difference in terms of photoactivity. What about the visible range? You can see that for visible range, these particles that comes from the colloid also show a very interesting signal in photoactivity. So this result looks very interesting because remember that these particles give the best performance for the PFAS degradation. Of course, we have to understand more what we can learn about the TRMC signal and so on. This is under progress. So to conclude, I hope we have shown that nanodiamond can be considered as a photocatalyst under solar light for hydrogen production and PFAS degradation. We focus on the photoactivity of the particle to be able to understand more what are the involved mechanisms. And we know that the nanodiamond water interface plays a key role in all these reactions. So the levers to enhance the absorption in the visible range Of course, you can use the surface chemistry as we have shown here, but you can also induce some sp2 carbon at the surface of the nanodiamond. This is a work under progress. We didn't have time to show it, and we have interesting results in that. And of course, the third lever would be to dope the nanodiamond with nitrogen, boron, and to see what is the impact on the properties. So in terms of perspectives, we are working with 3 PhD students at the present time. The two first are really focused on hydrogen production and PFAS degradation. So Yasmin is synthesizing nanodiamond metal nanoparticle hybrids for that, and she worked on our setup. And in parallel, Ferdinand is investigating what sonochemistry can bring in terms of surface modifications. And in parallel, we try to have our own source of nanodiamonds using CVD. This is something we started with a master student, and Raphael now is working during his PhD on that to be able to tailor the size, the shape, the doping, or even the color centers. With that, we would like to acknowledge our students. So Marie, Raphael, who performed the PFAS study, Marie, a lot of study on the TRMC and the material we use, Loris for all the milled nanodiamond work and colloidal stabilization, Christian for the UPS XPS study, our colleagues at CEA, for Caroline and Sophie for the PFAS study, important contribution, Olivier and Marc for cyclotron at Soleil, Jocelyn for XPS, the Strasbourg team for hydrogen production, TRMC with Christophe, our colleagues from Versailles for the UPS, from Simtech for the high resolution TM, colleague from Soleil synchrotron, and from abroad, Arsène, Tristan, and Alon for the NEXAFS measurements. Other colleagues abroad are funding, and with that, we'd like to thank you for your attention. Thank you.
Thank you, Jean-Charles. Thank you, Hugh. It was excellent presentation. So much new information and so many to think about. Very exciting results and how to explain. Continue to dig out what are the core properties of detonation versus HPHT milled nanodiamonds. Can be most impactful in different sectors of applications. It's excellent. Thank you so much.
Thank you.
And we are open to the questions from the audience. Just unmute yourself and start asking, or you can raise. Please, Leonid Shigiley from Virginia.
Thank you.
University of Virginia.
Yes, thank you very much for the very interesting presentation. So you described it very nicely described how surface states or surface chemistry can be modified by annealing, and then solar type light nanodiamond interaction can be used for catalysis. And my question is it possible to use more intense light, for example, radiation by ultra-short laser pulses to modify defect structure of colloidal nanodiamonds and maybe trigger some carbon-carbon bond rearrangements, affect sp2 fraction, or perhaps even melt and resolidify nanoparticles, colloidal nanodiamond by rapid heat transfer to water environment? Would it be a viable technique for for modifying the particles?
This is an interesting approach, I would say. To be honest, we will probably do it by annealing and then dispersion in water. But of course, using leather would be interesting to have some in situ modification. In terms of efficiency, I don't know if it's efficient or not. Perhaps Olga have some view on that. That the laser efficiency to induce sp2 in colloids. I don't know the efficiency, but the approach seems original and interesting.
Okay.
And Leonid is an expert in laser ablation simulation.
Okay.
So he works in depth and he worked with carbon materials also. So maybe we can consider further
This is true,
discussion out of the
we also have, I think, in attendance, Amul Gupta from our university. So he is an expert in experimental modification of colloidal particles as well.
The point will be maybe just to add a few words on that. The point will be also to keep the colloidal stability of the system. And so we know that applying a annealing treatment on this kind of particles, very quickly we lose the ability to keep the particles in colloidal suspension. So maybe using a system which is directly done in colloids, like with the laser system or something like this, could be a very nice way to very smoothly modify the extreme surface of the particles, keeping a large part of the particle intact with the colloidal stability, but just adding a little bit of sp2 carbon defect, whatever you want at the surface. Yeah, definitely.
And it could be probably a way to have an in situ selection, because the less graphitized will stay in suspension and the other one will sediment. So this is also something convenient.
Yes, and absorption itself can be different for different types of particles. Yes, so it can be more selective, I guess.
Yeah, it's an interesting suggestion for experimental research. And our next person to ask is Nadezhda Bulgakova. Nadezhda, please ask your question.
Thank you very much. Actually, thank you very much for very interesting talk. Maybe I missed this information. I'm sorry, but we know that catalytic activity is very dependent from size of nanoparticles. What were sizes of detonation and mill nanodiamonds, and how efficiency of catalysis depends on that?
Very important. Excellent question. I would say for the detonation nanodiamond, you know, the primary size is around 5 nanometer. You got still some aggregation. In the data we presented in water, you have something like using DLS, something around 40 nanometer. So it means there are some aggregation. And the point for the mill nanodiamond, I didn't stress it in the lecture, but of course, you know that they are highly polydispersed. So it means that the sample we use for the studies, we didn't select in size for the moment.
Yeah, and
so still can be a factor for user optimization.
Yes, definitely. True, because you have seen that the particle which works the best for the degradation of the PFAS is the hydrogenated mill nanodiamonds. The same than Jean-Charles showed that finally in colloids they form very long chains. So this is also important to consider, because if you want to make the degradation of the molecule, you need also to have the molecule which is adsorbed at the surface or really in the vicinity. So what happens when you form these chains to the adsorption of the PFAS, and then also with all the size of the particles we know. So this is something that this is maybe just the beginning of the story. And
perhaps to answer that, we developed some method to sort out milled nanodiamonds. This was the work of Marie during her PhD. This is quite successful to isolate different populations. It's not completely monodispersed, but the point is that we got quite low amount of each. So then to be tested, but according to the concentration we use,
experiment could be nice. We should try.
Okay, great. Next question comes from Stefan Stelnik. Stefan, please ask your question.
Thank you, Hugues. Thank you, Jean-Charles. It was really beautiful talk, really touching to me, because I'm doing similar things. And I have a question regarding the PFAS and the interaction with the nanodiamonds. How important is actually the positive zeta potential of the nanodiamonds with the interaction with the P4A, right? Because it's an ionic compound, as far as I know. So how important is quite probable electrostatic attraction between these two? compounds? Thank you.
Yeah. This is a very good question indeed, because we worked on that. So first, to look at the stability of our nanodiamonds in the PFAS. So in our case, it was PFOA. So the stability, of course, because we have seen that if we increase too much the concentration of PFOA, of course, we lose the colloidal stability just by too much adsorption of the PFOA at the surface of the milled nanodiamond. But at the same time, we have to keep in mind that usually what is said for this very long chain is that this is the hydrophobic interaction which are really important for the very long chains. And as you know, the hydrogenated milled nanodiamond, you know this very well, is quite a weird surface because it keeps the hydrophobicity but are still stable in water. So we do believe that when we have the long chains, maybe this is the hydrophobic surface of the hydrogenated milled nanodiamond which help the adsorption. And what is said is that when you decrease the size, then finally this is the more polar part which will play on the adsorption, and then after we may have the adsorption by more, let's say, positive, negative attraction.
I see. Thank you very much.
Thank you. We have next question from Abe Walcott. Abe, please ask your question.
Very good. Thank you, Olga. A fantastic presentation. Thank you very much, gentlemen. It's a nice merger of things that I've done in the past, diamond work and photoelectrochemical water splitting. So typically when we would do water splitting, we would do thin films and use potentiostat to do current voltage work, as well as wavelength dependent work to understand our current based on wavelength. Do you see yourself doing some of that work in the near future with both the detonation nanodiamond and milled nanodiamond, whether or not it's hydrogenated or oxygenated, to get more in-depth information about the mechanism and wavelength dependent photocatalyst information? Thank you.
Well, definitely, yes. We need to go into this kind of characterization. So here, of course, we are dealing with colloid, so we just need to put the particles on the electrode. So this is not so easy because there is a lot of question about how to make a good adhesion, how to have a very good transfer while keeping the surface of the particle accessible. But this is something that we need to do to better understand, yes, the behavior of our nanodiamonds. Yeah, true. This is true. And so we are really open to make any collaboration on that in the future.
Very good. And to follow that up, as you're doing the photocatalytic work, you have your cell and you're illuminating from one side and then going into your GC to look at your byproducts. Are you noticing any type of time-dependent precipitation where your nanocrystals are settling out, or have you done any type of quantification about precipitation mechanisms?
We did not notice real, let's say, real aggregation of the particles according to the time of exposure. Really, the suspension remained very clear. We are something between 0.2 to 1 milligram per milliliter. So this is concentration at which we are able to see the particles directly, and we are not able to see any modification of the aggregation state of the nanodiamond. So I mean, we are not able to notice it. Of course, we should look at this with the DLS, for instance. But I'm quite confident that that should be okay. Yeah.
Very good. Thank you so much.
You're welcome.
Do we have any more questions? Please unmute yourself. I have a question. Are you planning to continue to elucidate a role of nitrogen? We know it's very big difference in nitrogen concentration and detonation nanodiamonds and HPHT, and it's possible to mill CVD diamond plates to nanodiamonds, and there will be almost no nitrogen. As a control experiment, for example.
Definitely, it's an important parameter. Of course, we discussed already together during the diamond workshop at Saclay in October. We need to find other sources of nanodiamond by probably milled from different films with different nitrogen content to check what is the role and the impact on the properties. That's true. This is something we have to do. And this is something we would like really to achieve perhaps with our own bottom-up synthesis, to be able to play with the nitrogen in the particle and then to measure on the setup we have just close to it.
And how much material do you need to make these basic measurements, say go, no go conclusions? How many milligrams of material?
No, this is not very much. If you want to look at the hydrogen production, we just put let's say so far this is 1 milligram for 80 milliliters in the photoreactor, so 1 milligram per experiment. So you can see that this is not that much. And for the PFAS degradation, this is yes something like few milligrams each time. So this is yeah.
Then we will also think on a source of, say, no nitrogen nanodiamonds.
Yeah, would be very useful. Yeah, good.
Okay, it seems it was a lot of people today, almost 50 visitors for your lecture, and it was great in-depth presentations, discussions, and we are looking forward to continue to enjoy playing with nanodiamonds, with the application as a community. So it's fascinating material and brings a lot of scientific joy. So I wish everyone very exciting 2026 in terms of discoveries.